Signore e signori, ladies and gentlemen, good afternoon and welcome to today's webinar dedicated to scientific culture and to the cooperation between Italy and the US in the field of scientific cooperation, organized in cooperation with the Italian Scientists and Scholars in North America Foundation, ISSNAF, and with the Consulate General of Italy in Chicago. I would like to welcome and thank very much for their participation to this talk, our distinguished guests and speakers. Cinzia Zuffada, President of ISSNAF and Associate Chief Scientist at NASA's Jet Propulsion Laboratory. Welcome. Giorgio Bellettini, Honorary Professor in Physics at the University of Pisa and Guest Scientist at Fermilab. Welcome, Professor Bellettini. Paul Grannis, Distinguished Professor Emeritus in the Department of Physics and Astronomy at Stony, Brook University. Welcome, Professor Grannis. And Thomas Botzios, Consul General of Italy in Chicago. Welcome, Consul as well. I would like to remind you that this talk is being recorded and it will be available soon on the ISSNAF website and on the Italian Cultural Institute in Chicago YouTube channel, and that we are also streaming live on Facebook. During the talk and after the talk, Professor Grannis will moderate a Q&A, and I kindly ask you to type your question using only the Q&A button at the bottom of your screen and not the chat window. And you're most welcome to type your question during the talk so that Professor Grannis we might include your questions in the conversation. Finally, I'm very pleased to leave the floor now to Consul General Thomas Botzios for his welcoming remarks. Please, Consul, the floor is yours.
Thank you. Thank you, Director Di Vito. It's a great pleasure for me being here, and I would like to thank ISSNAF, particularly Presidente Cinzia Zuffada and the Italian Cultural Institute in Chicago for the organization of this event, focused on the great historical and future-oriented cooperation between Italian scientists and researchers at Fermilab, where, by the way, I was a couple of months ago for an exciting visit, thanks to the warm hospitality of Director Lockyer. It is an honor for me and privilege to welcome Professor Bellettini and Professor Grannis, to whom I'm gonna leave the floor soon. Allow me to make just some brief remarks to outline how the outstanding cooperation between Italian physicists and Fermilab is the best testimony of the great bilateral cooperation between Italy and the United States of America. And we're very proud of that, particularly this year that marks the 160th anniversary of the diplomatic relations between our two countries, established back in 1861. As I said, this long-lasting cooperation is now more than ever vital and open to the future, with so many projects linking together Fermilab and other important American laboratories and research centers with Italian counterparts. Just for an example, the National Institute of Nuclear Physics, the INFN, and the Gran Sasso laboratories, for example. As it was stated just yesterday in a webinar held in our embassy in Washington, DC on the dark matter, the scientific cooperation at the international level is the best approach to address the greatest challenges we are facing in this period. Science-based solutions are and should be the answer to the most challenging issues, which involve the future, the wellness and prosperity of all the human beings. If this is true, and I'm convinced it is, we all must be thankful to scientific cooperation. And the Italian factor at Fermilab is one brightest and outstanding example of such kind of cooperation. So the Consulate General of Italy and the Italian Cultural Institute stands at your side and would be happy to cooperate with ISSNAF and the Cultural Association of Italians at Fermilab to spread the Italian language, music, and culture in the United States. Thank you.
Thank you, Director Di Vito, and thank you, Consul Botzios, for your very nice introduction and very generous work. I am grateful for you to hosting this seminar. We are ISSNAF, and we will present a very special legacy story here on a trajectory in high energy physics today. With the support of the Italian Embassy, ISSNAF started this series to feature prominent experts in their fields, widely distributed on the North American territory, who also serve in leading roles in the ISSNAF organization through a collaboration with the Consular Network and the Italian Cultural Institutes. So today we share with the public the reflections of Professor Giorgio Bellettini, one of the original founders of ISSNAF and a member of its honorary board of directors. He is also the founder of the Cultural Association of the Italians at Fermilab, which has recently become a chapter of ISSNAF. So with the objective of leveraging the good work of a community local to Fermilab and give it more visibility at the national level. To engage Professor Bellettini is Paul Grannis, Distinguished Professor Emeritus in the Department of Physics and Astronomy at Stony Brook University. He was the co-spokesperson of the D0 experiment at the Fermilab proton-antiproton collider in 1995, when the CDF and D0 collaborations discovered the top quark, the heaviest constituent of matter. He was awarded the 1990 Panofsky Prize by the American Physical Society. And without any further ado, I thank you all for participating, and I give Professor Grannis the floor.
Thank you very much, Dr. Zuffada, for inviting me to come and do what I have enjoyed for many years, and that is to have a conversation with Giorgio Bellettini. Giorgio was a student at Scuola Normale Superiore in Pisa from 1953 to 1956, and received his laurea cum laude from University of Pisa in 1957. He joined the faculty in Pisa in 1960 and had an appointment as research scientist at CERN in Geneva from 1963 to 1965. And from 1974 to 1976, he was the director of the Laboratorio Nazionale di Frascati. From 1968 to 74, Giorgio was the spokesperson of the Pisa Stony Brook experiment at the CERN intersecting storage ring proton-proton collider, which made the unexpected discovery that the total cross-section, measuring the size of the interacting protons, grows with energy. From 1980 until today, he has led a consortium of Italian physicists working at the Collider Detector Facility experiment at the Fermilab proton-antiproton collider in the western suburbs of Chicago. And under his leadership, the Italian groups contributed many of the critical components of the detector and software systems that are needed for analyzing the data. While he was the CDF Co-Spokesperson from 1995 to 97, the experiment co-discovered the most massive elementary constituent of matter, the top quark. Giorgio returned as co-spokesperson in 2015 to 2016, while the final analyses of the data were being done. And in recent years, he has stimulated the Italian involvement in several other frontline experiments at Fermilab. Giorgio has received numerous honors, including the Prize for Physics from the Italian Minister for Science and Technology, Fellow of the American Physical Society, Commendatore of the Italian Republic, and the Carlo Matteucci Medal of the Italian Academy of Sciences. In addition to his many scientific achievements, he has for many years led programs for joint Italian physicists and engineers participation in research projects in the US. And I am delighted to become an honorary Italian for the day and join Giorgio in this conversation. Our paths have intertwined for 50 years, starting with work at CERN in the 1970s, and continuing with the friendly competition for many years on our experiments at the Fermilab Collider. So, Giorgio, Let's start with the 50 years ago when the first collaboration that you made with an American group, the total cross-section experiment at the CERN ISR. Tell us how this collaboration came about and what did you expect to learn from that experiment?
At that time, there was a problem on what the total proton-proton cross-section would do with increasing energy. All the hadronic cross-section which were measured with beams in the laboratory showed that the cross-section was decreasing and basically becoming constant with increasing energy at the initial energy of the ISR, which was the first proton-proton collider being built, and it was going to be the top energy machine in our field for a while. So one could say, fine, there's very little to understand if we want to show that something which is becoming constant. Actually, however, I'd been working for a few years at CERN with a smart scientist, an Italian, who lived in America for a long time, Giuseppe Cocconi, who in fact was an expert in cosmic rays. And he was mumbling with me, discussing that there may be something strange in those cascades initiated by the cosmic rays in the Earth's atmosphere. And in particular, the new phenomena could happen there. And he was not even so sure that the cross-section was constant at those tremendous energies. However, it was difficult to measure because of these cosmic rays have a composition that not all of them are protons, and they have a spectrum in energy. So it is difficult to understand really whether the cross-section is growing. So listening to him and thinking to the aspect of the cross-section, I was actually wondering whether one could learn something by studying these cascades, by producing the cascades on the Earth. Because if you are on the Earth, on the laboratories, two protons which hit on top of each other, as it happens in the collider, then the cascade which has the aspect that you see in this picture, this is a cascade initiated by a cosmic ray. In fact, at the ISR would take the aspect of two showers, mostly forward, downstream that each beam.
Excuse me, Giorgio.
All the secondaries available for measurement.
I think you need to be sharing your
Yes.
screen if you're talking about some pictures. Can you share your screen?
I think I think I've done it before. Oh.
There we go.
Yeah, in fact, okay, sorry.
Now,
Well, I was flashing
screen.
quickly through the ISR. Okay.
And click the full screen.
It should be okay now.
We see the screen, but you can make it full screen. That's it.
I have full screen.
Everything good. Thank you.
So the connection is slow. Okay, so let me then show a little bit first the plot of the ISR. This is an intersection region of this collider, proton-proton collider, which was reaching 32 GeV in the center of mass. This one machine, one ring of magnets, hitting another one, and at the center, of course, there was in a vacuum, the vacuum tube of the machine, vacuum pipe of the machine, the interaction would take place. So you can imagine that mimicking the cosmic rays, but in the center of mass, because we are here in the center of mass, the secondaries would go mostly left and right along the two beams. Some of them will be large angles, but after all, you have the space available, and you could try to cover all the angles and catch all the particles and count basically all the interactions. And if you count all the interactions and you know how intense the beams are, you know how well they overlap at the crossing point, you can work out the cross-section directly, which is the number of events per unit luminosity would directly give the cross-section. So this is what I had in mind. and therefore we designed an experiment which is briefly shown here in the sketch on the right, on the top of the right. You see the two beams and a number of counters at the center of the intersection, and the cones of counters left on the left beam, similarly on the other beam. And below under this sketch, you see the an artist's view of the counters, which of course show that the counters are split in sectors, azimuthal and polar sectors.
You'll need to go to the next slide. You need to
see to count it.
Go to the next slide, Giorgio. You have to show the diagram.
Okay, so this you mean this slide here, the detector, the picture of the experiment?
We're there. Now you've switched. Fine.
On the left, you have the. Okay, I see. So there is some slow in the communication. So on the right, I was showing the sketch. On the left, I saw a picture of the experiments, which was quite sizable. You see the counters downstream one beam, the central box, and on the right, on the back, you can imagine that there is a similar set of counters as on the left. And here in the next slide, you have in fact a better picture which shows precisely the counters downstream one of the beams. There is a similar one, an identical one actually on the other side. Well, this is a situation that we found. On the left. You have a plot of the various hadronic cross-section, mesons, neutron, protons. They all were going to become. They looked like they were flattening with increasing energy. On the right of this of the energy on the right corner of this plot corresponds to the minimum energy of the ISR. So if you go to the right plot is ISR data. And the ISR data run basically the PP cross-section is shown again on the left. This was the previous one measured on the floor with an external beam. And the ISR data are repeated many times. They are seen that they show a clear increase of the cross-section. So this was a big surprise because it's nothing against the basic principles, but it is a surprise because it was not expected from the previous data. If you make a model which was very popular at that time, so-called an optical model, in which you imagine that one proton is a sort of black disk against which the waves impact, and everything which is it's the disk within its radius r gives an interaction, whether it's an elastic or inelastic, but it gives a contribution to the cross-section. The total cross-section in this model is twice the surface IR square, is twice the surface of the disk. So this is simple. The only parameter is the radius in this formula. So if this is the total cross-section grows, it must mean, in effect, in practice, if you want to be simple, the radius of interaction is growing with energy. Why is that happening? Because it was a 10% effect, enormous. There was nothing clear, no new single process which would interact, possibly be responsible for that use effect. And even today, how did we feel with you? Or you had truly, yeah, I called once.
That's fine. I was going to ask you what you were talking about. There's a picture that I recognize, and let me ask you this: in this first experiment that you did with Americans, how did the Italian and American groups complement each other? Were there differences in the style of their doing physics? Or were there frictions due to the fact that the Americans entered after so much of the apparatus had already been built by the Pisans?
Actually, you know, Paul, I believe that the beautiful start of this experiment in a collaboration with Americans probably had an enormous influence in all my following career, because see, too, the detector was basically built, and I called Guido one evening in America, proposing to him to come and set up this detector and have it running and look for physics together. He was a beautiful person, very, very, well, you know very well, but very unique, smart and calm and very deep. And he came with a group like you, people like you, all of them very professional, very competent, very serious, not pretending, but simply doing things perfectly. So my experience was what they say. I don't know if I made a theory out of it, but certainly I felt like that collaborating with Americans was just fantastic. And in fact, I sincerely believe that the reason why we have been able to run so smoothly with a so well organized and checked and calibrated detector was in good part your merit, certainly on equal grounds as the Italians. So the start was beautiful, not at all. Did you have the impression, I ask you now, did you have the impression that the Italians felt you were intruding? What? How did you feel? You were well received?
Absolutely. We we had a tremendously good time. Sometimes we found that we were in between some of the subgroups of the Pisa group that were battling perhaps a bit, and we were the buffer, but that was fun as well.
Yeah, that was fun because there was people like you who were calm and trusted by everybody. So you had a function of calming down the fights, and effectively that was an excellent contribution also.
Now, I think in many ways the ISR was sort of the turning point in the way experiments are done in high energy physics. At the beginning, the experiments were rather simple and had a rather fixed number of goals. And then as time went on, they became more complex. And I think your own experience there, starting with the Pisa Stony Brook experiment, but then going on to a much more complicated experiment, was indicative of that. So what was your next step at the ISR after the Pisa Stony Brook?
During my measurement there, our measurement there, I got convinced it was nice, but many nice and simple and somehow pictorial feature of these events came out of our data. But the data were insufficient if you want really to go deep and understand the physics, deeply the physics of the data. So I felt that in order to do better, one should have complicated much the technology of the experiment and get not only position of tracks, but also curvature of tracks, momentum of the charge path, energy, name it. And so at the very end, you imagine that rather than having a beautiful, elegant, cigar-shaped detector, counter-made detector full of bins of counters, you would have a similar detector, but each bin would tell you the energy and the type of the particles. Much more complicated. And there was no way for Pisa to face such a major job. And also at that time, I was appointed director of Frascati, and so I would not be able to have the group much smaller. Same thing was at CERN and trying to get into one of these areas that we were occupying, and he wanted to measure muon pairs, searching for a very high mass new object that possibly could be there. And this is sort of physics that he had been doing for a while, also at Brookhaven. And so it turned out that we found an agreement. There was a messenger by Sam, was a lady, Saulan Wu, who was very calm and competent, and she somehow discussed with me all the details of a possible collaboration. At the very end, we concluded that we could actually make a big detector as Sam wanted, which would be built with the help of CERN, And he would just look for the muon pairs produced in these events. And we would, a tradition of the Pisans, study the entire structure of the event, possibly very close to the center of the interaction. And so the agreement was made that he would build, we take care of the detector and of the main detector, and we would somehow take care, the Italians would take care of the tracker, the central tracker. So the idea of the experiment that was proposed and approved was called R209, search for the Z boson, which was supposed to be the carrier of the weak interactions, and the group was this combination of my former ASR group and the SEMTIN group. And the detector that you see here, on the left, you have this usual, let's say, artist drawing of the main detector with lots of absorbers around the interaction region with magnetized slabs of iron and in chambers, measuring the filtering the muons. There is a track here, which very thick track is supposed to be a muon pair, detecting, measuring the muons, which would only be the one able to penetrate so much material, and measuring the momentum as well. And at the center, there was a very delicate rigged vertex detector built by Pisan. So we, in fact, we love the idea of measuring the details of all the details. Possibly do better for this track, but in any case, not lose any single branch, prong of an event. That was a sort of attitude at that time. This is what this answered your question. Okay? So I was intrigued because it was necessary.
Fine, I think
and because I was going to Frascati.
Let's go on to your time in Frascati, but let me break here. The comment that I made that the Stony Brook group was a buffer between competing factions of the Pisa group elicited a comment or a question. What do physicists fight about anyway? And I would respond to that. Well, physicists fight about almost everything. Everything is up for questions and for grabs, and there's a lot of friendly competition. But then there was another comment from a student, David Lloyd Owen, in the Pisa Stony Brook experiment that has a very warm recollection of the relationships between the two groups and the enormous welcome that the Americans were given in joining. Let's take a step forward to the time that you were at the Frascati director, when once again you were at the center of a major discovery. This time it was the discovery of the J-Psi particle, both simultaneously, both at Brookhaven Lab and at SLAC in California. And it became apparent, I think, that Frascati could add something to the story, and actually did so in a record short length of time. So can you take us through that saga of the early days of the J-Psi discovery?
Yeah, there were many details that I don't have time to go through. But first of all, this you see on top of this slide, November 11, 1994. This is called in our field is called the November Revolution. There was a tremendous discovery both at Brookhaven, the same thing, and Sauer group, and at SLAC with the Richter group. There was a discovered new particle which was very strange because it was very narrow, which means very stable, and of an enormous mass, which was about 3.1 GeV, which means close to 4 protons, very, very, very big. And they was called the J. It was observed at Brookhaven in the effective mass of two electrons, yes. And of course, Saulan knew that at Frascati, my laboratory, had an electron-positron collider. So this particle could have been produced in the annihilation of these two particles. Actually, but in fact, that was how it was discovered at SLAC. So she wondered, she called me immediately. I think on the night of the first day when they announced it publicly, saying, but Giorgio, do you think that you can look at it? Of course, in principle, that was out of our range because the maximum energy of our machine was 3 GeV, you see the lower sentence here. And so it was dangerous. You could burn some magnet to do some disaster by going beyond the design energy. But in that situation, we decided to do it. And we tried, and very properly, in 1 day or so, the collider was able to reach reach the energy and find a new particle. And what was nice that in a few days we collected the 3 experiments working on a day. Each one had, of course, a different intersection, but each one saw the resonance. So they added all the information, and in a few days we were able to write a paper, which was very interesting because of the extreme novelty. And then I was in touch with Saulan. I transferred all the information to her, and he helped us tremendously much because at the very end, she was able to get printed, typed, and properly typed as Brookhaven, our paper with our plot, and get it printed. They get it published together with the 2 discovery papers of DNL and of SLAC. And this is what it was. On the left, you see you see the peak discovered at Brookhaven on the floor, production of 2 electrons. On the right, you see the peak measured at Frascati on the same PRL issue, one after the 2 discovery paper of SLAC and DNL first, but our paper next, considered as a confirmation, which was an enormous, very nice things that Saulan and their group made for me and for us. So again, you see, I could not live with the MIT group because I was not a CERN anymore at that point. But again, this attitude certainly confirmed the impression that these Americans are great. As long as you work hard and you are good enough, you can share a beautiful experience with them. This was a unique case of that I think somebody was able to do for me.
So running a large organization like a national laboratory is a very different matter from conducting an experiment with a small number of like-minded people. What kind of adjustments did you have to make when you were the director?
Well, let me then just show this next slide, which is the results of the R209 experiment, which showed again the J psi peak. They were looking for muon pairs, and this is effective mass distribution. And they saw also another less evident, but certainly sure peak, which was called the upsilon, which was another particle very similar to the J psi, but a larger mass, which had been discovered in those years, in fact, in 77. And so that came out with no new discovery because the upsilon, not only the J psi, but also the upsilon had been discovered already. But the point was that the Z that was discovered years later at the CERN collider was too heavy for the ISR. And so this data came out in the meantime. And in Frascati, as you say, I was confronted with the picture of the standard model of subatomic particles which are coming out from these massive data arriving one after the other. And I tried to picture this in this plot, which is a sort of a Lego. On the pink area are the quarks, that are those that compose the matter, basically. On the left, you have square named U, another one below a square D, a cube named D, which are the up and down quark that are hidden in the proton and in the neutron, of course. And there's a doublet. And in fact, the symmetry is such that these fundamental particles come in doublet with a difference in electric charge, but the same interaction otherwise, the same constants of interaction. So in addition to a doublet, there was another doublet recently discovered because there was a mysterious S quark hanging around since a while, but with discovery of the charm, the C quark, you had another doublet. So two doublets. Then with this upsilon, it turned out very, very easily. It was understood that it was a very similar case as the charm, but as a J psi, it was a bound state of two new quarks that were called bottom of beauty. A quark is an anti-quark. So in order to allow for the theory to function, and in order to explain the properties of production and interaction of this B, it was clear that it had to be just himself as well, a partner of a doublet. And the other doublet, member of the doublet, which was called Top, was not known. It had to be found. Otherwise, it meant that all this huge construction, a very pretty, very elegant, very symmetric, would collapse. So everybody understood that the top had to be there, that to be found, and it was really obvious to continue searching for pairs of leptons, and because after all, the charm was found as a J psi, the beauty was found as a upsilon. Why not as a top? And so at that point, the idea was to continue. I said, well, what can we do? Shall we look for the top? But it was very clear that it was not possible to do anything from the start because the machine was very, very resolved. The energy machine was not even good enough for the charm and for the psi, and we had no way to embark of a large investment. You asked me, how was it? It was very difficult, actually. It was very exciting because of this start. This happened within 1 year, not even a year after my arrival. So very excited. You felt at the top of the physics of our era, but then you discover that you can't do much because the laboratory is not strong enough. And then I considered collaborating with Carlo Rubbia at CERN because at that time it was pushing for an experiment on the SPS, turned into a proton anti-proton collider himself. And in fact, that is where I discovered the Z later on. But he was too advanced. There would be no time for me to really contribute. So going to CERN was late for me. And in that time, towards 1978, 79, there was a discussion of turning, even at Fermilab, the proton synchrotron of that laboratory turning into, or using it to create somehow a collider rather than for producing external beams for experiments on the floor. That looked like being difficult, but at least new. There was nothing yet, just drawings, the idea, enthusiasm. And so I decided to marry that chance. And I found an agreement with Alvin Tolestrup and with a Japanese group headed by Unitaka in Tsukuba. And I had a look at the laboratory, who looked like this. Of course, CDF and DD were not there yet, but this is nice to show because also the area of Fermilab is very attractive. And this, at least on the Italians, I believe, had a significant impact on their at the very on growing, feeding their enthusiasm to go to there. Good physics, nice people, beautiful area. Anyway, this is where I decided to go. And,
So,
and the idea there was to design a cluster.
So can you
Well,
tell us about what
okay,
what
that is
your
what
tell us about what the Italian groups were able to bring to the CDF detector. I know from my own point of view,
yeah.
one of the things that we envied most about CDF was the existence of this novel silicon vertex detector, which played so strong a part in the discovery of the top. So show us a little bit about what the Italians were able to do.
You see, since you go to a place where everything is new and you find a strong collaboration with the US and with Japan, then you have to design a detector, and so we are free. And so I felt at that occasion that I could fulfill my dream of building around the CDF really a complete, strong detector in which you had all the solid angle covered, covered in beams of angular, of apolar and azimuthal angle, but in each beam you would measure particle composition, nature, in energy. So this is in fact this sketch shows the detector of the first generation, the central box, 2 cones, nothing new, but you also see in the central box an idea of the splitting of the detectors in bins, both at large angles and in the forward direction. And this was the entire conception of the detector. We designed in 2 years, 1981, the so-called this first generation CDF detector. There was 13 institutions, 56 Americans, 15 Japanese authors, and 60 Italians, so about 80 people. And so it was a three countries that in our idea, that was a 3-country collaboration. We brought mostly a number of significant, because we were supposed to be the experts at that time. We came from CERN, already experienced on the Hadron Collider. So in a way, we had some experience. And here is a list of the most important things that we contributed. The Hadron calorimeters, which was a huge system of very massive calorimeters in which we built everything. The miniaturized Vertex detector, again, building on the sort of tradition that we wanted to see very well what was happening at the vertex of the events. Then trig electronics, we had a number of experts in there. Of course, we collaborated with others, in particular with Berkeley. For spectrometers, we collaborated with Tsukuba. For spectrometers, repeated the total cross-sectional measurement at the ISR, which was again part of our history. And in fact, we measured also the total cross-section with CDF, and we found again that was growing a lot, much more than it was doing at the ISR. And also large size muon counters to cover the whole solid angle. Now, here you see in 85 the picture of the central magnet, which was the first to be ready in the assembly building with 3 flags: Japan, US, and Italy, and which showed that this experiment was born as a 3-nation collaboration. And this is a nice picture in which you see one half of a ring, of a quarter of a ring of central calorimeters, all made an assembly of wedges assembled in a Roman arch. And this is one wedge, which is seen from the light pipes and the various slabs of scintillators that you have to read. This shows again the idea that these wedges are all pointing at the intersection. So again, you have sort of an eye in which you look directly in the direction where you are. You look directly at the source, and you try to reproduce the experiment as in your detector as it was born, which was a very big, huge complicated stuff, but it was big. And also, again, coming back to the story of the mini vertex, this is the sketch in 81, at the very beginning of the design. It was a sketch of a so-called silicon vertex detector, 4 layers of imprinted electrodes on a silicon substrate, again with XY readout, which would be arranged in a drum around the intersection. And simple, but the technology was new, was never used at the Hadron Collider. It was pushed very much by Aldo Menzione, who for that received later the Panofsky Prize, because he had used this technology in a fixed target experiment on the North area of CERN, and this discovered measuring the delayed decay of charm hadrons. And the idea was that one could do physics of the heavy flavors, charm, the beauty hadrons, by again catching immediately a few millimeters away from production possible secondary decay vertices of the events. And this is what it was, in fact, one of the important contribution, probably the most important contribution of the Italians to CDF. This is CDF, the vertex was split into 2 parts, and at the end of one, in the year 2000 or so, this was replaced in CDF in the second version of the vertex, and these 2 parts were recovered. One was sent to Pisa and saved in our archive, and one was saved at Fermilab. So, and this is when actually in the year 2001, when the catch for the top started. This is basically, does it answer to your question?
Yeah. So I was wanting to go on now to the top discovery, which presumably is the most notable achievement that CDF made during the Tevatron era. Why was the finding the top quark such a big deal, and what role does it have in defining the current paradigm model of particle interactions? And in particular, what should we make of the fact that its mass is so very much heavier than all of its fellow quarks?
I don't really know, but let's go through the history. In fact, after discovering the bottom quark, this problem of the third doublet, in which we discovered only one component and we wanted to find the other one, that was named tentatively top. This started immediately after the finding of the upsilon, and this is a picture of what happened in a number of experiments in number of accelerators from 85 to 91. It was found that the top did not exist, and that its mass at the very end in 91, it was concluded that its mass had to be superior to 77 GeV. So much more than the beauty. Actually, much larger than the W mass. And this is a very serious problem, because this W is the carrier of the charge carrier of the weak interactions. So it's, in fact, the top would be produced, ideally, the idea would be that the W would decay into this doublet. Is coupled to the doublet, so it would decay in the beauty and in the top. But the top is too massive, so it cannot decay. Then it can be produced together with the beauty. So actually, the W became possibly a decay product rather than the father of top production, a son of top, together with the beauty. At the very end, therefore, in a strong interaction, you cannot produce a quark without the anti-quark. So if you look for the quark, for the new top, you have to look for a pair of top anti-quark that each one would decay into the W and the beauty. So two W's to beauty. The W's are unstable. They decay, for example, into leptons, into quarks. At the very end, you get a very intrigued six-body final state, and you have to find a new particle. You can, in principle, as long as you catch all these products, you work the momentum and the energy, which one of them, the relative angle, you can build the total energy, total mass, the effective mass of this complex six-pronged state. But then you can imagine how difficult it is. So that is why Top became so famous. Our problem was made relatively easy in a way. We had this, the detector worked very, very, very well. This, for example, showed displayed on the surface of the calorimeters, the energy of the calorimeter cells, displayed in a plane where the azimuth and the polar angle are flat in a plane. This is how a jet of particles in which one of these one is jets, which comes in our case from the decay of W, would appear. So they are a fairly concentrated bunch of energy. Some of energy is in the front section of the counter, which is called the electromagnetic. The other one is blue.
Giorgio,
part of the cascade.
Giorgio,
yeah.
let me interrupt just for a moment here.
Yes.
We're coming rather close to the end of our allotted time for conversation. So if you can speed up this discussion about the top, and then after that, I want to go on to some final episodes in your career. So let's try to move along a little bit at this point.
So anyway, see, you're right. I will do my best. So these are how jets appear, and of course you have to use this information. This is the jet seen on the sideway. This is the jet longitudinal. So this is, for example, instead how the tracking around the vertex appears, in which you have several jets to continue, of course, that would continue in the calorimeters. But you have also two jets show very clear a secondary vertex. So these jets are tagged, are likely to be quark initiated jets. So you have to reconstruct with this sort of information, this total picture that I told you. And at the very end, this was came out, at least for CDF. We obtained a convincing result with a modest statistic, but enough to proclaim the discovery in 95. And this was the CDF. At the same time, D0 also found very much the same, around the same mass peak. And so the conclusion that we could announce the discovery of the new particle. This is a picture in which we were taken when all of us, myself and you, and the other spokesperson of your collaboration, D0, Hugh Montgomery, and Bill Carithus was spokesperson with me, and John Peoples, the director of the laboratory. So this was a ceremony at the very end. The token was discovered, and why is that so heavy? I don't have the site. This is a presentation of the so-called pictorial. The size of the symbol is proportional, roughly, to the size of the quark. So the charm and the beauty become visible, and the top is enormous. So why is it so large? I do not know.
Well,
then we also worked on. Well, yeah, you want to discuss the top, right?
Right. There are those who say that the top quark is actually the only one that has a natural mass, because it's about the same as the Higgs boson, or the scale of energy at which the electroweak interaction is broken, and that all the other quarks, the light ones, are the anomalies. Who knows? It's a mystery that we still are trying to get to the bottom of. I think at this point we need to go to the last phase of your career, and let me ask you about your recent efforts over the last 10, 20 years, where you've switched some of your focus to strengthening the ties between the American and Italian communities at Fermilab and across the US, and to develop mentoring programs for young Italian scientists. So how did this change in emphasis come about? What makes you proud about these activities? And what do you think the impact of them has been on young people in Italy?
Yeah, let's see. This is the last show of what we did for CDF. In run 2, the most important things was developing a trigger which would be able to select the beauty quark, beauty hadrons from the others and create samples of clean, heavy flavors physics. And for this, Luciano Ristori with Aldo Menzione got the Polansky Prize. But then true, some other important results were obtained. They are listed in this slide, which will stay for the record. And also at the end of CDF, the CDF was shut down in 2011. And I note that over the history, we had 5 non-American co-spokespersons, which were all Pisa scientists. Then
that's impressive.
What happens after that? It happened that this good atmosphere, yeah. After that, we had a couple of experiments which are running now. One is called G-2. They all are refined difficult experiments looking for anomalies with respect to the standard model. They include Italian physicists. For example, this anomalous, this measurement of the muon magnetic moment has shown interesting results a few days ago. The other one is a measure of the possible, not expected at a significant rate in the standard model, but possible conversion directly of the muon brought at rest in a solenoid into an electron. Again, this includes many Italian physicists, and that is also ongoing at the moment, being built. But the most important contingent of Italians are going to go into the neutrinos, and in fact is also in particular thinking this long-term neutrino involvement that I'm trying to draw your students. The neutrinos, there are several neutrino experiments going on since a while at Fermilab, but there's a new one coming using the technology of the liquid argon, which was proposed years ago and realized with a detector operated at Gran Sasso for a while, a 600 tons liquid argon detector named Icarus, which has been refurbished recently at CERN and brought to Fermilab. And this unit is already at Fermilab now. And there are something like 40 or 50 Italian physicists working on this project. This project, this neutrino detector based on liquid argon, will be employed in particular in a cavern in South Dakota, in Sanford, at 1,300 kilometers from Fermilab, where not very soon, take years before it's built, this detector will look for anomalies in the neutrino features. And this is a sketch of the underground areas with 4 huge 10,000 tons each liquid argon detector. And of course, at the moment, just the caverns are being excavated. And of course, the last sentence here says, many new students will be needed for the success of such a long-term investment. So then now I come with a little detour. I come to answer your question. Why am I caring so much about the students? Well, I founded years ago, not so much, 15 years ago, a cultural association of Italians at Fermilab, with the idea to let the Italian culture known better than it is now, that it was in the American community. And I started with musical events, painting exhibition, conferences, and so on, teaching Italian. And in particular, since a number of years, KAIF, since this birth actually, KAIF, this cultural association, runs a summer student program that we started in Pisa very, very long ago to really raise students for our group, for our CDF groups. Now, at the moment, there are 3 scientists. One is a scientist of the technical division in Fermilab, myself. Another one is a professor in Pisa, who take care of recruiting and finding training for these students. Now, we find the training programs at Fermilab. We look for students, we interview them, we put them in touch with the supervisors, and at the very end, they're paid by the laboratory for 2 months in summer, and they spend 2 months hands-on on the local experiments. This process is very interesting, I believe. In color, you have the annual, in some rate, the scale is here. You have the number of, each year, the number of physicists. Very few for many years. Then, the few here, the green are the students, the physicists, you see. Originally, until the year 2000, but basically, the students were all physicists. And then they flattened a little bit. But with the arrival of Emmanuel, actually, the engineers, the blue ones, started taking grade. And now, recently, we have about 25 students per year, as many engineers as physicists. We had an enormous success in particular here, which was but anyway, this is fine. Order of magnitude, 25 per year, 2 months per year, as many physicists as students, as engineers. This is a picture in a particular area, very nice bunch of young people. When they come, they really create a particular Italian atmosphere and feeling on the entire village. And then I here mention what I'm doing now, since we entered in ISSNAF. We are started again by Zoom, remotely, teaching Italian. It's going on already. So everybody who likes to connect via KAIF and ISSNAF to us can listen to these lectures. And we are now getting have an agreement, digital agreement with the Conservatory Luigi Cherubini of Florence that will record for us concerts of classical music, and they will be offered free on the KAIF and ISSNAF websites. I'm next only. I only one slide left, which is just a conclusion. But I want to answer to your question. Why am I taking care so much about the students? Basically, it's a long story. I have an enormous esteem of the merits in intelligence course, college, of the youth. So I think that all of us have been better essentially when we were young. Thinking to this project, which are going to take dozens of years for being completed and produce physics, who can be, what is the staff that you should try to train and recruit and get, if not the smart students of today. So this is why I am taking care so much, and I'm so proud, I must say, of the success of this student program. It's looking forward to the future for Fermilab, but for Italy, for all the fields. We have to increase very much the emphasis on recruiting young people. Now, the last slide is, can I give this concluding slide?
Of course.
Eccola qua. It says, first of all, it expresses appreciation for this warm welcome that KAIF received in ISSNAF. Recalls to you that our Italian community in Fermilab is long-standing, and we started with early experiment even before me, but it had an enormous boost with CDF in the 80s. And I gave you a few examples. of showing you how the collaborative experiments and Americans at Fermilab have shown that the bonds between the two communities are naturally sincere and very strong. And finally, my hope is that the KIFE student program will help ensuring again the duration from time of this creative US-Italy friendship.
Well, thank you very much, Giorgio. It's always a great pleasure talking with you, and I very much hope that we'll do it again soon and do it in person. It's been a nice revisiting of your career and, in fact, also my career. Let me just ask one question that came in from the audience from our friend Claudio Pellegrini, who asks you to say in a few words what you think the future of high energy physics will be. Does it hold for us a very large hadron collider, an electron-positron collider, or should it be focused on the intensity frontier and the study of things like G-2 and rare processes like the neutrino interactions? Where are we going?
First of all, let me say hello to Claudio.
Yeah.
This that is there. Well, I cannot predict the future. Nobody can. My taste does not go in favor of the high precision experiments because they cannot believe at the very end, understand the clue of they can find the anomalies. They can, of course, strengthen our decision to look deeper, but you have to find something new if you want to understand something real. So I am in favor of new accelerators. Now, among the accelerators, I say which one? Electron collider, proton collider. I am surprised that in the years, a design which was born in America and supported for a long time by very smart American accelerator experts like Bob Palmer, Alvin Tolestrup, and so on, which was a muon collider, that is not pushed with strength and with emphasis by the American community. It is rejuvenated, it's being rejuvenated a little bit now all over the community, but it's really dumbed down. And we need time, and we need to do something difficult, exceptional. I think it's clear that it is not impossible to build a muon collider. Why is it dumbed down so much? Now, I come in part, I think, to comment on your request of a future. What is the future of our field? This is because the future of our field is not necessarily bright, because the politics is not behind us so much anymore as it was after the end of World War II. And people just believe that if you insist that for pure science, for really understand as much as you can about the universe, you want to do something very difficult and very hard, and somehow commitment to government to spend money on you for many years is difficult to get approved. So conclusion, Claudio, nobody can tell what is best. I certainly would favor a collider. I am surprised that we do not shoot for a muon.
Well, it is certainly an interesting idea, but it is also one that is not yet fully demonstrated. So we have lots of work to do to remaining to us. With that, Giorgio, let me thank you again, and to thank ISSNAF and the opportunities that you have given for this conversation. And I turn the conversation and the program, the webinar, back to you, Dr. Zuffada.
Thank you. Thank you for a very, very interesting exchange, very thorough exchange. It has been very enjoyable. We have had a very attentive public, right? And engaged. We have had a few questions. So thank you so much for sharing all of these beautiful trajectory with us. And thank you, Director and the Consul, for the hospitality.
Thank you. From the Italian Cultural Institute in Chicago, and also on behalf of the Consulate General of Italy in Chicago, I would like to thank Professor Bellettini and Professor Grannis for his passionate and conversation, which gave us also your personal perspective on the decades of research between Italy and the USA. And also I would like to thank very much President Cinzia Zuffada